So let's take example here. Let's just take an ordinary QD. Okay. The Lagrangian is simple. Okay. Here, photon mass is protected by the Ward identity at the Hamandu. Okay. So the gauge symmetry is protecting the photon mass. So then delta m photon remains 0 because of the symmetry of the photon. And if you compute the electron mass correction, it is protected by chiral symmetry. So if you compute this one, this loop function delta m psi is proportional to m psi itself. Some loop function. Okay, it's proportional to itself because of the chiral symmetry. This is what I said. Now let's do something else. Now if you do scalar QD or Ikawa theory, scalar Ikawa theory essentially. You put you can do it with scalar QD or you can do it with Ikawa theory or any other theory, and use dimensional regularization. Okay, the corrections. Okay, scalar QD. Plus Q. Say for example, let's write something like this. Some theory. L theory is equal to del mu phi bracket del mu phi mu. And now let me also put scalar LQD also. And then there also let me also couple some y psi bar psi phi. Okay, I put it two interactions, but let's look at one by one. Now, if you look at fermion photon masses, the same arguments hold true. Look at the corrections to the scalar masses. Scalar masses will have corrections of this type. This type, so on. Okay, and then there also are corrections coming from proportional to fermion. If you look at the scalar corrections, for example, delta m phi square is proportional to m psi square. So it is proportional to the highest momenta in the theory. Here also, this one will become the highest momenta in the theory because it's a derivative coupling. This will be proportional to the highest momenta in the theory. Okay. If you put a cutoff, this goes as. So the scalar mass correction is not proportional to itself. It is proportional to the highest mass in the theory. If m psi is the highest mass, it will pick up the mass of the cell. This you can do it in dimensional regularization. You can do it in dimensional regularization also. It will always pick up the highest momentum scale. The scalar mass is always sensitive to the highest momentum scale in the theory. So, in terms of Ikawa theory, it will pick up the mass of the fermion. In scalar QED, it will pick up the highest moment as well, whatever it is, the scale of the experiment or whatever it is. Okay? It always picks. So it has nothing to do with whether you are using cutoff, dimensional regularization or not. This is what I think I am against what Anish Manohar says. Okay, I will suggest you guys read Ramesh Kaul's papers on cancellation of quadratic divergence. This was precursors of supersymmetry. These are people were looking at various toy examples and how scalar theories behave under one-loop corrections. I will send you these references. This is explicitly done by his in his papers. It's not very highly cited, but it's actually pretty well done using dimensional regularization. And then there are this Kaul Majumdar famous papers on cancellation of, along with Witten they have done it, on cancellation of quadratic divergences in supersymmetry. So if a scalar theory is not protected by any symmetry, so it will always, at radiative corrections, will always push it, or it will be always be sensitive with the highest mass scale in the theory. If it couples to heavy fermion, okay, you can say this one I will use dimensional regularization and somehow renormalize this. Okay, agreed. But if you have a coupling with a very heavy fermion, it will always pick up the mass of the heavy. It could be a very heavy gauge boson also. Okay, it will pick up the mass of the heaviest particle in the theory if it couples to it. The heavier the mass it couples to, okay, that correction it will always take into consideration. Okay. This is the point I was trying to make. Now, what Fayez is saying that suppose if the Higgs doesn't couple to any heavy particles and it only couples to standard model fermions, is there still a hierarchy problem? Okay, and you ignore gravity. Okay, if there is Higgs doesn't couple to any other particle. Okay, and if you ignore gravity, there is no hierarchy problem. There is no manifestation of the hierarchy. Let me put it this way. Because you cannot ignore gravity, you cannot ignore the scale of gravity. So if the Higgs doesn't couple to anything, say for example, it just remains Higgs as it is. It doesn't couple to anything, it just has a simple potential. Okay? And it has, we are living in a metastable vacuum and all that, what we learned in standard model, it's all true. Okay? But there's still one more problem. Okay, I will come to that in 1 second. So, what I showed to you is that if you assume that there is a high scale, either a granulification scale or a Planck scale, okay, or just an extra fermion which is coupling to the Higgs, okay, the Higgs corrections will always pick up to that scale. If none of this happens, as Fayez says, there is no manifestation of hierarchy. There is no manifestation of hierarchy. Okay, but is it true that there is no gravity, there is no quantum gravity, there is no gauge coupling implication? That is the result thing. Okay, that we have to we don't know actually. Okay, we'll think about it. Now there is one more thing I wanted to point out. We have talked about the Higgs potential a little bit Finally, why people don't like the Higgs system as it is that suppose if I know the Higgs mass very accurately, 126, say 145.9, dot, plus dot. I know it super accurately, imagine. Then what I mean to know is that this potential should be super accurate in the universe. So precise. And it should be stable so precisely under any small perturbations. These perturbations could be quantum corrections. Okay? So it should be so precise. How does it one manage to maintain it so precisely? Is there a God, somebody sitting there in the universe, setting up the initial conditions and maintaining these things so precisely? Okay? This is one of the questions one can ask actually. Why? How is the Higgs potential maintained so precisely? Okay. Is it so precise? Is this the only possible potential? Okay. Who is maintaining it so precisely? Because every physical system in the universe should be stable. But should it, if it remains stable under quantum corrections, so even at the tiniest quantum corrections, it may be possible, but that means that these are the only possible quantum corrections and there are no other corrections such that it's always stable. I listed out all the top corrections, no? The top or gauge corrections and so on, so last time. Are these the only possible corrections? Or is there somebody sitting there and maintaining these corrections such that this potential such that the universe nicely rolls into this and into the stable state and remaining stable? So, this is also one of the reasons you want to say something.
There's still a problem with the exponential is not stable at high energy.
Right.
The function.
Yes.
So if we consider like the early universe when energies were comparable, we have metastability. We could have a runaway direction.
Right.
Problem.
Yes. Now, there is no way of putting this Higgs potential into any known inflationary models or any early universe models. It doesn't work. We have no way. Okay. As of now, we have no way of putting this potential in any known things. Okay. And stability we talked about. Actually, last week I talked about it. I talked about the metastability and showed the body. So many people don't like the idea of spontaneous symmetry. Okay, spontaneous symmetry breaking may be very good in lab systems, but whether the universe actually maintains it and how does it maintain it? It could be something like a dynamically driven spontaneously symmetry breaking. So some interactions are driven, setting up this potential such that you're doing this. Okay, we'll come to such examples. Okay, so but anyway, any questions about the hierarchy problem? So far, what I have discussed.
When you discuss this gut theory in the hierarchy problem in context of gut theory, so this is because this coupling are like the unifying at that state, and we are so in order to explain we are proposing this gut theory.
Yes.
That is why this hierarchy problem is arising.
Yeah.
So if it is the artifact of the gut theory that we are making.
No. The hierarchy problem manifests itself because now there is an instead of a you forget about quantum gravity now. You have a granification theory because you think that all the couplings are unifying, so there must be some bigger theory there, which has only one coupling. Standard model is not a unifying theory. It has three couplings. As I said, it's separately, I think in the first class itself as I mentioned. Standard model is not one theory as people say, it is three interactions, three couplings, so on and so on. Okay? But the grand unification theory is only one coupling. It has only one coupling, which is one structure for all the quarks and electrons. Okay, they're all sitting in some 10 and 5 bar multipliers in 3 generations and so on. So now in that setting, the hierarchy problem manifests as the splitting. How do you generate standard model Higgs compared to the triplet Higgs? I said there is the 5 bar and 5. There are 2 Higgses. Okay, some combination of them, some linear combination of them, becomes the standard model Higgs, another becomes the triplet Higgs, say for example. Okay. The point is that this has to remain at a scale which is 100 GeV, whereas this will get a mass scale around 10 power 15 GeV or something. Okay, but they are coming from the same multiplier. This is called the doublet triplet splitting problem. Okay, now you can maintain it at the tree level potential by fine tuning the potential. We derive this condition. Say that I put mh is equal to, because the masses are dependent on the potential. The potential is a long potential, the gut potential. The gut Higgs potential is complicated because it has 3 Higgses, so it has a 24. So you have to write 24 times all the possible couplings between the 3 Higgses and everything. It's a complicated potential. So it could have a vacuum in which one of them gets a Higgs mass, 50, mh is called 100 GeV, another gets a mass around GeV, and there is a 24 also, which gives you masses. The web of the 24 gives you masses to the Goldstone bosons are absorbed by the gut gauge bosons, which are called eccentric gauge bosons. So they get absorbed. But the remaining Higgs have to maintain this mass hierarchy between them. One is sitting at gut scale, another between. Now, if it's not sitting at gut scale, it can lead to rapid proton decay. So it has to sit at gut scale. Okay, gut symmetries break baryon and electron. Okay, so this, now when you do a one loop calculation of the potential, again the mass correction to the Higgs is proportional to the empty mass square. Okay, so it is getting corrections proportional to the highest mass square. So again, you have to fine tune at the one loop level. Somehow the potential cancels off this large correction. Okay, so one loop FD potential will again generate a large.
True for any gut theory.
This is true for most gut theories, unless there is non-supersymmetry. I am talking all in non-supersymmetry gut theories. This doesn't happen in gut supersymmetry.
That's what my question was, like whether it's the effect of beyond standard model theory. So gut theory is a beyond standard model theory.
Gut theory is a beyond standard model. Yes, simply.
Yeah. So it's not like
no
standard model artifact or something.
No. It is manifestation on the standard model Higgs. It's a manifestation on the standard model Higgs. Standard model Higgs, the hierarchy problem corresponds to the radiative corrections to the standard model Higgs. The standard model Higgs is not protected by any symmetry. So if you extend the standard model, if you don't, first example, you don't extend the standard model, but derive the standard model from a quantum gravity theory, then it has corrections proportional to the Planck scale. Second example, I put the standard model in a grand unified theory instead of a quantum gravity theory. Okay, in that example, it also gets corrections proportional to the gut mass scale. Okay. Third example, I don't care about gut, I don't care about quantum gravity. I just couple with a heavy fermion. In the third example, if it couples to a heavy fermion, it gets a correction mass proportional to the heavy fermion. Suppose if it doesn't couple to any heavy fermion, why do you need a heavy fermion? We'll see examples with the neutrino masses. Okay. Okay. So if it doesn't couple to heavy fermions, if it doesn't live in a grand unified theory, If it doesn't see the quantum gravity theory, somehow it exists without seeing quantum gravity theory, then there is no hierarchy. Otherwise, there is always a hierarchy. Okay.
What happens to that X and Y gate bosons?
They are living at gut scale. They have masses around m gut scale.
They are responsible also for supposed proton decay, and you'll hear people putting searches on the mass of these gut scales from proton decay lifetimes. There's many searches going in that direction.
Yeah. X and Y gauge bosons should be at the gut scale. If they come a little bit below, it will lead to lots of problems. They lead to a lot of problems like proton decay and other things.
Similar to the muon decay where you have the W boson and tau, essentially it's the same thing.
Because X and Y bosons have couple quarks to leptons. Okay. There is one more point I forgot about anomalies today, but anyway, I'll come to it. See, I said one point I wanted to mention before I lose that one. So I said baryon number, lepton number are anomalous in standard model. Like gauge anomalies, we said that they get cancelled. But the global anomalies, if you gauge them, they become anomalous. Okay, like baryon number, lepton number, they are anomalous things. So you cannot gauge baryon number and lepton number in standard model. But you can gauge some combinations of them. So these combinations are non-anomalous. Li minus Lj. These are non-anomalous. And second one, which is more famous, okay, these are non-anomalous. So they can be gauged and you can make a consistent quantum field theory. This is in the part of the anomalies which I forgot to mention. Now, if you want to, now regarding flavor symmetries also, we'll come to it when we discuss flavor symmetries. If you impose a flavor symmetry, you have to make sure that if you impose any UN symmetry or any extra symmetry with the particle content, you have to make sure that they should be non-anomalous. If they are anomalous, I said they lead to problems because the theory is non-anomalous. But there are ways of taking which are anomalous at low scale, but at high scale they are non-anomalous. We'll discuss them in some very specific theories. So these are mechanisms called Green-Schwarz mechanisms and stuff like that. Where a theory which looks non-anomalous at weak scale is actually anomalous at weak scale could actually be non-anomalous. The full UV theory should be non-anomalous.
Isn't that violate the anomaly matching? You should have
So of the anomaly matching conditions.
yeah, because you match the UV to the RH.
That's only true for semi-simple groups. Yeah, that's a tooth anomaly matching condition. But that is for confining groups. So if it is if it is non-confining, you can have Green-Schwarz mechanism. You can have extra particles. If you have new degrees of freedom, it's no longer valid.
So, like, this is a little bit weird because essentially anomalies are really very measure the integral.
Right.
Integral.
No, if you have new degrees of freedom, like axions.
Okay, so like essentially you introduce new degrees of freedom.
You introduce this, so then tooth anomaly matching conditions will not be valid. So axions are valid at high scale, so you cancel the anomalies. This is essentially the Green-Schwarz mechanism.
I'm actually don't know much about
Okay,
I
alright.
don't know anything about that.
Okay. Okay. So any further questions today? Either regarding hierarchy or
In this ordinary theory, so we are writing this mass term of psi bar and psi. So does it have a chiral symmetry? I mean, because
QD as it is a vector theory, but psi bar psi is always a chiral theory. Okay, psi bar psi is always this interactive. It always matches left with right. So any corrections to mass will always have to break this chiral symmetry. Okay? So the mass term is actually chiral breaking, chiral symmetry breaking. Okay? So any correction to the mass term should always break chiral symmetry, so it's proportional to itself. In QED. But Higgs mass term, okay, see it this way. Fermion mass term, the moment mass goes to 0, you have an extra symmetry, e power I gamma phi. Okay? Higgs mass term, set mu square goes to 0, there is no extra symmetry in the energy. Okay? Say for example, L fermion, m goes to 0, you have a new symmetry in the theory, some alpha also. But if you have mu square h square, okay? Now mu square goes to 0. Is there a symmetry in the theory? No, there is no extra symmetry in the theory because the Higgs is invariant. The scalar theory is invariant. It's always a radial part, no? H dagger H. Any unitary transformation is always invariant. So there is no extra symmetry you can put it on. Whereas here you can put an extra symmetry. The scalar is always a radial part. Okay, there is no e power alpha beta you can put it in because it's always r square. Okay. It's like a mod of z square. So there is no extra symmetry which can come for scalar theories, unless you have symmetries which are, we'll come to it, which are like supersymmetries.
So here, so the example that we saw in this third case, so there is Higgs correction, Higgs mass correction from the fermion. Here this m psi is a large, heavy fermion.
It's a heavy fermion.
Okay, so
It can be any fermion, but in the limit m psi goes to infinity, the Higgs mass also goes to infinity. Okay? Say for example, you don't have, say for example, here, if you are setting m psi, it's in the fermion case, delta m psi is proportional to m psi. Okay? So m psi going to infinity doesn't make sense because the correction goes to infinity in the same way. So the left and right are the same thing. Whereas in the Higgs, this is a different parameter altogether. It's a different parameter altogether. So you can set this to very large, and this will go to very large. Yeah, even if it is 0, it goes to very large. So this led to one of the ideas that you can have Higgs mass starting from 0, the Coleman-Weinberg mode, to generate it completely from the top mass. Okay, it didn't work out, but okay, it doesn't work with the top values. The question is whether you can have corrections, and because of the fermion mass correction is negative, so you can generate completely from top mass, setting the mu square is equal to 0. Well, that's the Coleman-Weinberg, Eric Weinberg paper. Of course, it's famous for something else, but it's famous for the effective potential. But the idea started with this idea that mu square is equal to 0. Okay, you want to generate everything from the top potential, so that the dynamical explanation for the spontaneous symmetry. Okay, it's one of the first examples of dynamical symmetry. Okay. Yeah. Now, if you are still not convinced about hierarchy problem, ask them. Is there hierarchy problem or not? There is. Okay. Because there is a hierarchy of forces. there could be reasons why the Higgs should couple to living organisms. If it doesn't couple, if there is no gauge coupling unification, if you don't take these signals, you don't care about quantum gravity, there is no real hierarchy. I mean, at our scales, if you are living with our scales, you don't really care about it. And there are no reasons why you should couple to heavy formulas. Okay. If you are really focused on physics of our scales, okay, and the Higgs is not coupling to other things, then you can say that okay, there is. I don't know about gauge coupling implications. I don't know about quantum gravity.
It's coming to this. I mean, gauge correction that is always proportional to this lambda square, right? And
It's always proportional to lambda square, but you can always you don't use cutoff. Don't use cutoff. Use dimensional linearization. Then the biggest correction in the standard model, if you are using dimensional linearization instead of cutoff, is coming from the top mass. That's it. The Higgs mass correction is proportional to top mass correction, and that's the reason why the Higgs potential is so sensitive to the top. So all the plots are in the top mass plane versus the Higgs mass. Okay, all the cut. So the last example, you can forget about cutoff completely. You can just set it as dimensional linearization, and still you'll get it in terms of psi instead of a cutoff of If you coupled the Higgs Ikawa coupling, it will be proportional to the mass of the Ikawa, mass of the correction, mass of MW, mass of MZ. Okay, Higgs corrections will be proportional to them in dimensional linearization. They will be proportional to the Z mass, W mass, and the fermion masses. Okay. Yeah. Any further questions? Okay. So next time we'll see the other reasons why like, neutrino masses.